In these last two examples that we're going to work on, we are still talking about how to solve an exponential equation like the one that I have here. But unlike in the previous video where we maybe applied the one-to-one property, because I have expressions or exponential equations, expressions on each side of the equation I mean here, but I can't use the one-to-one property because the bases are not the same. And I cannot use the definition of logs to be able to rewrite this because of the format that we see here as well. So what else do I do? Well, I can perform an operation, the same operation on both sides of the equation and still stay within the bounds, let's say, of what is allowed in our math. So just like I could take the square root of both sides if I wanted to, I can actually take the natural log or the log, as long as I take the log of both sides. Now I tend to take the natural log of both sides, so that's what we're going to do. Now when I take the natural log of both sides, this produces the natural log of 7 raised to the 2x plus 1 equals the natural log of 3 raised to the x plus 2. This is going to allow me to get the variable x that's up here in this exponential position out of that and bring it down front using the power rule of logs. So this becomes 2x plus 1 ln 7 is equal to, same thing over here, x plus 2 ln of 3. So now the variable that I'm trying to solve for is out of the exponential position and it's outside of the log part. So we are going to now do the distributive property because that's what happens when we have something on the outside of parentheses and I want to remove parentheses. Keep in mind that when I take the natural log of 7, like if I did it on the calculator, I get back a value. I just get some decimal number. So keep thinking that this is just a number and I'm going to multiply it into each of these terms on the inside to remove the parentheses. So that's going to give me 2x ln 7 plus ln 7 when I multiply the natural log times 1 equals, on this side, I'm going to get x ln 3 plus 2 ln 3. Okay, now we are going to collect my like terms. Notice that I have an x. I have a term over here that has x in it, and I have a term here that has x in it. And I want both of these on the same side of the equation. So I am going to subtract x log 3 over here to the left. So I have 2x ln 7 minus x ln 3. Now, this natural log 7 and this 2 log 3 are both just numbers. So they are, in a sense, like terms as well. So I am going to subtract this natural log 7 over here to the right. So this gives me 2 ln 3 minus ln 7. The next thing that I want to address is still trying to solve for the variable x. Notice now that in this term I have an x and here I have an x. So I have an x in both of these terms that I can factor out. So I get an x times 2 ln 7 minus ln 3 because I am taking an x out of both of these terms. That's equal to the right side of 2 ln 3 minus ln 7. So again, we're still trying to solve for the variable x, and this is just a number. It looks like a big mess, I agree, but it is still just a number. And when we try to get the variable by itself, we divide off this number. So I'm going to divide both sides by 2 ln 7 minus ln 3. Divide that by 2 ln 7 minus ln 3. And the exact answer, not the approximate one, but the exact answer is this big mess right here. So let's just rewrite it. 2 ln 3 minus ln 7 divided by 2 ln 7 minus ln 3. And that's it. That's the answer that we would get, and that's the exact answer. Now if I want to get the approximate answer, that's when we put this whole thing in the calculator and get a decimal value. I do want to caution you though. I know students will sometimes think that they can cancel this 2 with that 2 that's above it. You can't do that because you can only cancel factors. And at the moment, the order of operations tell me that I have to do the numerator, perform something up here, subtraction on the numerator, and then subtraction on the denominator before I can ever divide. So don't be fooled into doing that. That's how we are going to perform or take the natural log of both sides of our equation to come up with an exact answer. Okay, the last one we're going to look at has 3 terms here equal to 0. I notice that 2 of my terms are raised to a power, and I want us, and this is equal to 0, and I have 3 terms. So all of that together makes me start thinking, can I factor this trinomial? And I can factor the trinomial into this. So I've got my sets of parentheses equal to 0. The first term in my set of parentheses comes from the first term in my trinomial. So how can I break up e to the 4x into 2 terms? Well, that would be e to the 2x and e to the 2x. And that's the case anytime I have an even power like this. I can break it up or divide it by 2, in other words. Break it into 2 different numbers, 2 equal numbers. Now let's go back to the signs. I know that if the second sign of my function is negative, then the signs down here have to be one of each, or opposites. And then I'm looking for the factors. Since this term down here doesn't have a coefficient, right? This has a coefficient of 1. Then I'm only concerned with the factors of 18 that are going to subtract to give me 3. And that's going to be a -6 and a +3. So now what I have are 2 equations, or 2 factors I should say, that are equal to 0, and I want to set each of these factors equal to 0 and solve. So the first one over here is e to the 2x plus 3 equals 0, and the second one is e to the 2x minus 6 equals 0. So moving with the left equation over here, I'm going to subtract 3 to the right hand side. E to the 2x is equal to -3. And I have 2 choices on how I can solve for the variable x here. I can take the natural log like we just did of both sides, or I could rewrite this using the definition of logs. So I'm going to do it using the definition of logs on this first one. Remember that that's where we said I'm going to rewrite this. This is the base e. So it's log base e, which is the natural log, of the exponent -3 equal to 2x. Okay, that's just rewriting this exponential equation in its log form. But we're trying to solve for the variable x, but you've got to stop right here for just a second. And the reason for that is because remember that the argument of my log function, right, the argument right here must always be positive. So because that is not positive, then we can stop and we can say that that the answer, the solution, does not exist for this particular problem. So we can just kind of cross it out. Now let's come over here and solve x in this second problem. E to the 2x minus 6 is equal to 0. And I am going to add 6 to the right hand side. E to the 2x is equal to 6. And because we're kind of practicing how to take the natural log of both sides, that's what I'm going to do here, just to be different. And I get the natural log of e. Remember, that's when it's log base e of e to the 2x, means that I just take the exponent part down. So this is going to just be 2x equals the natural log of 6. And that's going to be x is equal to the natural log of 6 divided by 2. That's the exact answer. And when I put that into my calculator, I'm going to get a decimal representation of 0.9. Okay, so the 2 examples that we worked on in this particular video had to deal with still solving an exponential equation, but I'm using log principles or log properties. I'm either going to take the natural log of both sides like you saw me do here, or I'm going to rewrite my exponential equations using the definition of logs right here.